Okay, ready. Do you guys have any questions before we begin? No? Okay, so last time we were talking about rational functions, okay? So let's finish that discussion today. And what we discussed was this special property that rational functions have, which we call vertical asymptotes, okay? Let me show you the theorem. So remember, the vertical asymptote is a line, the line x equal a is a vertical asymptote if whenever the values of the function, the values of the input x, whenever they get very close to this number a, the values of the function goes to the positive or negative infinity. Okay? If this happens, you have a vertical asymptote. And then what we saw is that to figure out vertical asymptote is actually pretty straightforward. All you have to do is find the zeros of the denominator. But before you do that, you have to make sure that your function is in lower terms. Okay? So what you need to do is factor the top, factor the bottom. If there is any common factor, you simplify. And once this is completely simplified, then look at the zeros of the denominator. Okay? Those values will be your vertical asymptotes. And also remember that sometimes you're going to have a factor down here, but then after simplifying, it disappears. If that happens, what does that mean? What do we have at that point, at the zero corresponding to that factor? We're going to have a hole in the ground. Okay? So you have to be mindful of that as well. And, we did a couple of examples of finding vertical asymptotes, so that's one important property. Now, the other one that I want to talk about is how to discuss the end behavior of a rational function. Okay? And let's take a motivational example for that one. So let's see. So first example that we're working with was x plus 2 over x squared minus 4. Okay, so end behavior of rational functions. So remember, this is for any function. So recall when we ask the question, what's the end behavior of a function? What we're really asking is, so end behavior of f. So what we're asking is, when x approaches positive infinity, what can we say about the function f? When x approaches negative infinity, what can we say about the function f? Okay, that's what we mean by end behavior. When the input is very big in the positive direction, what can we say about the y values? When the input is very small in the negative direction, like it goes all the way to negative infinity, what can we say about the y values of the function f? So we saw this for polynomial functions, okay, and then we saw that this is governed by the leading term of a polynomial function. Now let's see what can we say about the end behavior of rational functions. So example, let's say that we have the first rational function that we're working with, x plus 2 over x squared minus 4. Okay? So we know that this function, for example, has a vertical asymptote at x equals 2, and it has a hole at x equals negative 2, right? We analyzed this last time. Now, the question that we want to ask is, what happens when x is very big or when x is very small? All right, so can anybody tell me what do you think is going to happen to the y values of this function when x approaches positive or negative infinity? Say that again. Decrease. Okay, why? Because it's negative. Okay, let's see. Let's just think about it. So let's think about what happens when x approaches positive infinity. Okay. So here we're just saying that x is a very big number. Okay. So you think about it intuitively. When x is very big, this top here is going to be very big. Did you see that? Because you're doing x plus 2. So if this goes to infinity, the top is also infinity. Now the bottom also is very big. Now the point is that this guy is going to be bigger than this one because here you are squared. So when x is a million, this guy is already what? A billion, right? Or actually more than a billion, right? It's a 1 with 12 zeros. So in non-American countries, so anywhere else in the world, that's a billion. Now here is 1,000 million is a billion. You only need 9 zeros to have a billion. But in the rest of the world, you need 12. Why is that? Why do you think is that? I don't know why it is, but I think it's so that they can make people billionaire faster. Because I mean, why would you go? I mean, if you follow the pattern, for example, 1,000 when you use the word hundred, that's because, so tens is 1 0, okay? So thousands is 2 zeros. Then hundreds is 2 zeros. Then when you use thousands, what do you have? 3 zeros. Now you can combine the thousands with the hundreds and the tens. Once you have exhausted everything, like what is it, 999,999, you already exhausted all the numbers. Then you go to a new quantity, which is million. Now, before you move past the million, you need to exhaust thousands, hundreds, and tens. Okay? So all the millions, the thousands, the hundreds, the tens. And you can do that because if you have 1,000 million, you could keep saying 1,000 million one, 1,000 million two. So there's no reason why you should go to billion. Now, once you have, all the nines, like what is it, 11, once you have 12 digits of already everybody 9, then you need a new word. That's when you go to billion. That's how it works in the rest of the world. But somehow here, 1,000 million is a billion. Anyways, the point is that when this guy is very big, let's say 1 million, then this one is going to be either a billion or more than a billion, depending if you want to think about it in the American way or not. The point is that this is way bigger than this one, okay? Because we're squaring this number. So what do you think is going to happen to this fraction? What happens to a fraction when the top is significantly smaller than the bottom? What happens to the whole fraction? It gets very small, okay? So if you think about it intuitively, we should say that when x is very big, this function should go to 0, okay? The bigger x is, the closer it's going to be to 0. So this is the intuitive way of thinking about this, and the degrees of the top and the bottom are the ones that tell you this, okay? Because this degree is smaller than the bottom, that means the bottom is going to go faster, and therefore this is going to go slower. Now we're going to see this in a more systematic and, I guess, formal way, but this is the idea, that the degree of top and bottom are going to tell you how this function is going to behave, okay? So at the end of the day, we're going to write down a theorem that tells you just look at degrees, and the degrees will tell you what happens, okay? But let's try to understand this a little bit more. So, because I want to know what happens when x is very big, I want to modify this expression a little bit, okay? So in particular, because we're interested when x approaches infinity, if we assume that x is different than 0, because we're going to be far away from 0 anyways, I can go ahead and divide top and bottom by x, okay? So in fact, I'm going to divide by the highest power that I see, which is x squared. So I'm going to do x divided by x squared, 2 over x squared, and then, so every single term, I divide this by x squared, which is the highest power that we see. And let's simplify. So we get 1 over x plus 2 over x squared divided by 1 minus 4 over x squared. So as long as x is different than 0, my function equals this function. Do you understand this?
Pardon me, I'm sorry. This was left outside. I don't know if you want to somebody.
No, that's fine.
Thank you.
Thank you.
So as long as x is different than 0, our function is the same as this expression. The reason why we need to make that distinction is because this expression is not good for x equals 0. Do you understand this? That's a bunch of little fractions with x's in the denominator. But away from 0, these two things are the same. Now, this is easier to analyze. So what happens when x is very big? So let's see. Let's look at each of the terms. What can you tell me about this little fraction? When x is very big, what happens to that little fraction? Yes? So it approaches one number, to 0, right? So for x big, so let me say, so when x approaches positive infinity, then we see that the top is going to be, the first fraction is going to be a little 0. Does everybody understand this? The bigger x is, the smaller that fraction gets. How about the second fraction in the top? What do you think? What happens to the second fraction in the top? It also approaches 0. In fact, it does so faster than this guy. You understand this? This denominator is growing way faster than this one. You're doing square. So that's 0, and then following the same logic, then every single little term here approaches to the numbers that I just wrote. The point is that this becomes 0 over 1, which is just 0. Okay? So, by the way, what we're doing here is we're taking limit at infinity. Okay? But in calculus, you call it limit. Here, we are calling it end behavior. So by just doing this little trick, and you can always do this, you have the rational function, you divide top and bottom by the highest exponent that you see. What's going to happen is that they're going to have a bunch of fractions with x's in the denominator, except the term that have the highest exponent, that's going to have a number instead of that denominator. You understand that? And then all the fractions with x's in the bottom, they will go to 0, and then only the number will survive. Okay? So for example, in this particular case, we do see that everything on top goes to 0, so this is a 0 over 1, which is just 0. And I want you to see that even if you would have done as x approaches negative infinity, the same outcome will happen, right? If this goes to negative infinity, it will also go to 0, but with negative numbers instead of positive, but that's okay, it also goes to 0. This goes to 0, and this goes to 0, okay? So the same thing is going to happen. So we can see from here that as x approaches positive or negative infinity, the values of the function approach 0. Do you understand this? Whenever something like this happens, we say, because this is a number, we say that the line y equals 0 is a horizontal asymptote. Okay? So what does it mean to have a horizontal asymptote? It means that when you look at the end behavior, you get a number here. If the function approaches a number when x approaches positive or negative infinity, y equals that number is a horizontal asymptote. So we say here, we say that the line y equals 0 is a horizontal asymptote of f. Okay, so let me write down the definition, and then let's look over more examples, and then hopefully you will be able to understand the theory. So, for example, here you can see that anytime that the degree of the top is less than the bottom, this kind of behavior is going to happen. Do you understand this? If you divide top and bottom by the highest degree, which is the one in the denominator, and then everything on top will be little fractions, and then they're going to go to 0. Yes? So if the degree of the top is less than the bottom, you will always have the end behavior to be 0, therefore y equals 0 is a horizontal asymptote. Now let's do some examples in which the degrees are the same, and then another one in which the degree of the top is bigger than the bottom. And let's see what happens, okay? Because those are the three cases that you can have. But anyways, before I do that, let me write down the definition. So, definition of horizontal asymptote. Words here. So we say this is horizontal asymptotes. I'm going to abbreviate this by HA, okay? So we say that y equals b is a horizontal asymptote of f. Now, it doesn't have to be a rational function, okay? This is for any function. If the values of f, if they approach to b, so if they approach b, as x gets in the positive or negative direction. So as x grows, I would say just as x approaches positive infinity, or as x approaches negative infinity. So you already know what the arrow notation means. Remember, this means x is very big, and this means x is very small in the negative direction. Okay? All right, so that's what it means to have a horizontal asymptote. So now let's just discuss how we actually find this for rational functions. We already have a little hint that if the degree of the top is less than the bottom, it's going to be 0. Okay? So, sample, determine the horizontal asymptote, if any, of the function. And let's see, let's do f of x equals 2x cubed minus 5x plus 1 over x cubed minus 1. And then let's do f of x equals 2x squared minus 5 over x. Okay, so this is plus 1. Okay, so here we have two rational functions, and notice that these examples are slightly different from the one above. The one above, we had the degree of the top is less than the bottom, okay? In this one, we have the degrees are the same, and in this one, we have the degree of the top is bigger than the bottom. Okay? So let's see what the situation is in each of these cases. So let's see, for the first one. So we have the function 2x cubed minus 5x plus 1 over x cubed minus 1. And we apply the same idea that we did before. Because we're interested in n behavior, x is away from 0. So I'm free to divide top and bottom by x by 1, 2. In this case, we divide by the highest power. What's the highest power that we see in this function? An x cubed. So let's divide everything by x cubed. Okay? So again, let's make the note that as long as x is different than 0, we can play this game. So just divide everything by x cubed. Then we have here x cubed minus 1. You know, you divide top and bottom, then you're not really changing the function away from 0. Okay, so now let's simplify. And the idea here is that, you know, any other term whose degree is less than the highest one, which is cubed, what happens is that when you simplify, there will be x surviving in the bottom. Okay, that's why we do this. So when you look at x being very big in the positive direction or negative direction, those terms will go to 0. All right, so what do we get here? So we have 2 minus 5 over x squared plus 1 over x cubed divided by 1 minus 1 over x cubed. Questions? So now we ask the same question. Again, we're interested in the end behavior, so we want to know what happens to this expression when x approaches positive or negative infinity. So let's go term by term. So this one is a number, so that one is what it is, it's a 2. But now what happens to the first fraction on top? The 5 over x squared. What happens to this?
It becomes 0.
So this goes to 0, this one goes to 0, this one goes to 0, right? So it will be a 2 minus 0 plus 0 over 1 minus 0. So at the end of the day, let me stress this. We get 2 over 1, which is 2. Questions? So what is this telling you? What does this mean? Do we have a horizontal asymptote? What is it? So the line y equals 2 is a horizontal asymptote. Yes?
So in this case, you don't have to do a negative infinity.
It doesn't matter. If you do positive or negative infinity, the same outcome is going to happen. Because all of these little fractions, they're going to go to 0. So we get exactly the same thing. All right. Questions? Okay. So that was number 1. So now let's try number 2. Now for number 2, we have f of x equals 2x squared minus 5 over x plus 1. So this time the degree of the top is bigger than the bottom. Again, let's play the same game. Here, assuming x is different than 0, we divide by the highest power, which happens to be x squared. Okay, so what do we get here? So we're going to get 2 minus 5 over x squared over 1 over x plus 1 over x. Okay, so now we take our limit, or in this case, we look at the end behavior as x approaches positive or negative infinity. Again, let's go to 0, let's go to 0, let's go to 0. So we get 2 in the top and we get a 0 in the bottom. Yes?
Why is it that for the you had it as 1 over x?
No, it should be squared. Yeah. So then we get 2 over 0, right? So now remember, this is not really that we're dividing by 0. What this means is just a notation saying that we have something on the top that gets close to 2 divided by something that's getting close to 0. So this is something going towards 2 over something that's getting very, very, very small. Okay? That's what I mean by this notation. Now, what happens when you divide by numbers that are getting consistently smaller and smaller and smaller, and the top is kind of fixed? Notice that here the top is going towards 2. It's not going to get beyond 2. Now, the bottom is getting smaller and smaller all the time. So what happens to this fraction? When the bottom is getting very small? What happens to it? It goes to infinity. right? You have a vertical asymptote. This is what this is telling you. When the bottom is 0, what does that mean? You're gonna have a vertical asymptote. Think about the function 1 over x. So this is gonna go to infinity. So in this case, it's gonna go to infinity, and because we have a positive on top, and let's see, here you have to say, yeah, so here is either positive or negative infinity. If you want to analyze which one of the two is it, you have to do a sign analysis of the function. Like for example, we can say when x approaches positive infinity, both top and bottom are positive, so it's going to be positive infinity the answer. When x approaches negative infinity, then the top is still positive because the square, okay, but then the bottom is negative, so it's going to be negative infinity, okay? So what we can say here is when x approaches positive infinity, the function f will approach positive infinity as well. When x approaches negative infinity, the function f approaches negative infinity. If you do a sign analysis to this expression, which is easy. And let me just show you indeed, because now you may wonder, well, okay, it's approaching positive and negative infinity, but let's say that you want to know how is this happening, okay? So what sort of shape is going to have? Remember, the whole point is that we want to graph. This is a special case, okay? So, first of all, whenever the degree of the top is bigger than the bottom, this is going to happen. You're going to have positive or negative infinity, okay? Now, this right here is a special case. Why? Because the top is one more than the bottom, the degree. Whenever this happens, this means that this function at infinity, yes, it's going to have this sort of behavior, but it's going to have a linear behavior. So it's going to have what we call an oblique asymptote, okay? And to find this asymptote, what you do is you do long division. Do you remember how to divide polynomials? Yes? So you do long division, and then the quotient of the division is going to be your oblique asymptote, okay? Or a slant asymptote. So, let me show you here. So note, dividing top and bottom gives the following. So let's see, I'm gonna divide these guys. So 2x squared minus 5, I'm gonna divide it by x plus 1. Okay, so we're gonna have here 2x. So you multiply, so you get 2x squared plus 2x, and then subtract. So these guys cancel, and then you're gonna have minus 2x minus 5. Degree here is 1, degree here is 1, so we continue. So we do minus 2. So again, minus 2x minus 2. You subtract. This is gone, and then we get here a negative 3. Because the degree here is less than this one. This is degree 0, we stop. This is the remainder, and this is the quotient of the division. Yes? So this guy right here, this equation, this is a line. This, you're going to see, this is what we call the oblique asymptote. Because what does this mean? So then, this means as the function f, remember, when you divide, let me show you the whole. So when you divide this by this, what this is telling me is that 2x squared minus 5, I can write it as 2x minus 2 times x plus 1 plus my remainder, which is negative 3. Remember, that's what it means to divide. We talked about this one time. When you divide something by something else, what you're looking for is another quantity, so that when you multiply, you get this guy. Sometimes division is not exact, so what we need, we're gonna get a remainder. Okay? Like if you divide 8 by 5, I think I even talked about that. When you divide 8 by 5, what do you want? You want to write 8 as something times 5. Now, unfortunately, we cannot do that. So in this case, in general, it may be something times 5 plus some remainder, which in this case is a 1 and a 3. Okay? 1 times 5 plus 3. That's what it means to divide. Same thing for polynomials. So now, if I divide everything by x plus 1, then over here we have our function. This is the function, 2x squared minus 5 over x plus 1. And we see that this is going to be equal to 2x minus 2 plus negative 3 over x plus 1. Okay? So our function is exactly the same as this expression. Now, when x approaches positive or negative infinity, let's analyze what happens to the expression on the right. What happens to this little fraction when x is very big? So what happens to this? It's gonna go to 0 because the degree of the top is less than the bottom, right? So this goes to 0 when x approaches positive or negative infinity. So the conclusion is that the function f is gonna approach the line 2x minus 2. When x is very big, our function will look like this line. Okay, so the end behavior, yes, is positive infinity to the right, negative infinity to the left, just like this line, but it's gonna be linear. It's not gonna be quadratic or cubic or doing something weird. Okay, it's gonna be a line. We call this an oblique or a slant asymptote. Oblique or a slant asymptote. Now, I'm not gonna be asking you to find this. This typically you do it in pre-calculus, okay? But you need to be aware that when there is no horizontal asymptote, there is one more case that you should consider, which is when the degree of the top is one more than the bottom of this axis, okay? If the degree of the top is way bigger, you don't have an oblique asymptote either, and then you have a polynomial behavior, okay? All right, so I'm just doing this for completeness. Any questions on this discussion? So let's summarize what we have found. So horizontal asymptote means that when x approaches positive or negative infinity, the function gets close to a number. So the line y equals that number is a horizontal asymptote. When it comes to rational function, what we have seen is that the degree actually tells you what happens. If the degree of the top is less than the bottom, if you play this game, you will always get 0. Okay? So when the degree of the top is less than the bottom, the line y equals 0 is a horizontal asymptote. If the degrees are the same, then you will also have the horizontal asymptote, but it's not going to be 0. Notice that in this case, when we divide top and bottom by the highest power, what do we obtain actually? We obtain 2 over 1. And what happens to be 2 and 1? 2 is the leading coefficient of the top, and 1 is the leading coefficient of the bottom. And this will always be the case. When you divide top and bottom, the degree is the same. These x's are gone, you get the numbers here, and the rest will go to 0. Okay? So when degrees are the same, there will be a horizontal asymptote, but it's not y equals 0. It's y equals the ratio of the leading coefficients. Okay? And then the other situation is when the degree of the top is bigger than the bottom. In that case, there's no horizontal asymptote, and you have your behavior is either positive or negative infinity. Which one is it? Here is the situation. Just look at the ratio of the leading terms. Here you're going to have 2x. Okay? So it's going to behave just like 2x. 2x goes to positive infinity to the right and negative infinity to the left. That's exactly what this is going to do. If you want to be more precise, in this particular case, when the top is bigger than the bottom by 1, you have an oblique asymptote, and you can find it by doing division. Okay? And the quotient is the equation of your oblique asymptote. So that's the summary. I'm going to summarize that as a theorem. So theorem, this is about end behavior of rational functions. End behavior of rational functions. So let f of x be equals to, so this time I'm going to write it as a polynomial, okay? So p over q. Now p is a polynomial. Let's say it's a x to the n plus, I don't care about the other stuff. The other stuff, these guys right here are lower degree terms, okay? Plus lower degree terms. And then q of x is going to be b times x to the m plus, again, other stuff which I don't care. Lower degree terms. We never did anything with these lower degree terms. When you play the trick of dividing top and bottom by the highest power, all these things are going to go to 0 anyways. Okay, so we don't care about those. Suppose that we have a rational function. Be a rational function. And then n is the degree of p. And m is the degree of q. Okay? So then, remember, 3 things can happen when you compare these numbers. either n is less than m, n is equal to m, or n is bigger than m. Okay? In each of these situations, we have a conclusion. Then, number one, if n is less than m, that means the degree of the top is less than the degree of the bottom. Then what can we say? Do we have a horizontal asymptote or not? If this happens. Do we have it? Yes or no? Which one is it? What is it? Say that again?
Yeah,
And which one is it? What's the horizontal asymptote?
it would be, or no, the leading coefficient of alpha by the.
No, look at the case that we are. If n is less than m, then we have a horizontal asymptote. Which one is it? Yeah, I've been saying this for almost half an hour. Which one is it? Y equals 0, right? Then y equals 0 is a horizontal asymptote. So if n is less than m, then the line y equals 0 is a horizontal asymptote. Do you understand this? And this is both. As x approaches positive and negative infinity, we have this behavior. Now, number two, if this is not the case, let's say that n is equal to m, meaning the degree of the top is the same as the degree of the bottom. So here, you just look at these little numbers, okay? That's all you have to do. Look at those guys. If they are the same, meaning the same degree, then what's the conclusion? Do we have a horizontal asymptote? And what is it?
It's
A over B. Very good. So when the degrees are the same, we still have a horizontal asymptote, but this time it's not 0, it's a line y equals A over B. So you need to look at the ratio of the leading coefficients. Okay? The line y equals A over B is a horizontal asymptote. And then the third case would be that the degree of the top is bigger than the bottom. When this happens, then there is no horizontal asymptote. Okay? Then there is no horizontal asymptote. Now here we can say something of 3.1. If it turns out that in this case n is actually m plus 1, meaning the degree of the top is 1 more than the bottom. If this happens, then we have what we call a slant asymptote. Okay? Then the m behavior of f is linear, and so f has an slant or oblique asymptote. Okay? And then how do you find it? So oblique asymptote, which is of the form y equals mx plus b, and it is found by long division, and it is the quotient of the division P divided by Q. So you do long division, you divide, remember P is the top and Q is the bottom. So you divide P by Q, when you do this division, the quotient is the equation of your slant asymptote. This only holds if the degree of the top is 1 more than the bottom. Otherwise, meaning if the degree of the top is too big, so if it's more than 1 compared to the bottom, then there is no slant asymptote, and what we have is a polynomial behavior or a power behavior. Then there is no slant asymptote, and the behavior, the end behavior of f is the same as, so in this case, we're going to have that the end behavior of f is the same as the ratio of the leading terms of top and bottom. So a x to the n over bx to the m. It's going to have the same behavior as this one. Now, because n is bigger than m, this is really a power function. Because when you do n minus m, this is a positive quantity because this guy is bigger than this one, okay? And this right here is a power function, and we understand power functions now. So with this theorem, you can tell precisely what happens at infinity for rational functions, okay? You look at degrees. Let me repeat, if the degree of the top is less than the bottom, then y equals 0 is a horizontal asymptote. If they're the same, it's a ratio of the leading coefficients. So in those two cases, you have horizontal asymptote. If it's bigger than the bottom, then there is no horizontal asymptote, and then there are two situations. If it's one more, you have an oblique asymptote, and you find it by doing division. Otherwise, if it's too big, then there is no oblique asymptote, and what you have is a power behavior. Okay, it behaves like this power function. Again, we're not going to really worry too much about these last two cases. In pre-calculus, you will go more in depth into this discussion, but we are interested in being able to find horizontal asymptotes on that. Okay, but I'm giving you everything here just for completeness.